I'm Matthew from Alcmeon. I'm not going to try to sell you what we do. What we don't do is we don't do artificial intelligence. We do machine learning. So it's a small distinction, but it does matter. And what I would like to do today is to take some time to show you how you could build a tied topic extraction tool from random arbitrary textual data. So obviously we do a lot of text mining at Alcmeon. We have some fairly complicated tools to do that. Some of them use a lot of open source software with ad hoc algorithms. But today what I have done is take only open source libraries and build the simplest system I could with these open source libraries on an arbitrary data set to show you what you can do with 2 or 3 days of work and a couple of open source libraries. So that said, what I'm going to talk about specifically is, say you have a corpus of text documents. So 10,000, 50,000, 100,000, a million. It doesn't really matter because as a human, you're not going to read them all. And you're not going to look at them to understand what people are talking about. And what you want to do is have a computer do all this boring work for you. And the computer needs to tell you, people talk about football, they talk about immigration policy, and they talk about that other topic. And it's roughly 30% ratio between these 3 different topics. And if you want to look at the documents about football, here they are. This is what I want. It seems simple from a functional perspective, but if you want to make a computer do this, it's a bit more complicated because there are lots of very fuzzy things about what is a topic. Even as a human, different humans will have different definitions of topics. Some of them will want very broad topics like football, but someone will say football games with the FIFA World Cup is a different topic than football games in the French World Cup. So it's a bit fuzzy, and this is why probably you might be disappointed at the end of the talk if you look at the results for these algorithms, because probably they won't give you what you really want. And as I said, this is just the start of the problem, or I would say more the start of the solution. Okay, so from a very high level perspective, the way this works is you take a bunch of text documents. First, you tokenize them. So once you have tokenized documents, you generate vectors for every document. And then you have a magic algorithm that will take all these vectors and group them together and tell you, these 2 vectors look roughly the same. Maybe they talk about the same thing. So what this means is tokenization. It's a fairly simple thing from a very high level perspective. You take sentences as input, so strings, and you generate list of tokens. So of course, what is a token is a fairly fuzzy thing too. It will depend on, well, here for English, usually people split on spaces, sometimes commas, maybe parents. And then you start asking questions about, oh, well, accents in French. Do they matter or not? So lots of simple questions, but that are a bit tricky to teach to a computer. Once you have these tokens, you're going to generate vectors. So you take the list of tokens and you generate a vector of size m, where m is unspecified for now. And you fill it with zeros and maybe I would say floating point values, but here it's just zeros and ones for simplicity. And once you have these vectors, you generate k topics. So you have to pick k, the number of topics that you want to get. And you're going to generate a vector that is filled with values, integer values from 0 to k. Here it's 10. K is equal to 10, and the size of the vector will be the number of documents in your corpus. So it's fairly abstract. You can get the code for that presentation. And here is a very rough outline of what you would need to do to run the algorithm I'm going to talk about. So each of these lines corresponds to a single Python script. And I'm going to run through this in a bit more detail right now. So I needed a data set for this presentation. Obviously, I'm not going to share the private data sets we have. Twitter is magic. You can get the 1% public tweets all over the planet in real time. Simple API, it's free. So I took advantage of that. And last week, I ran this small script and collecting 1% of every tweet on the planet that contained the word France. 2 or 3 hours. And I collected about 200,000 tweets. So you can run the script, but be careful, generate your own app IDs, please. I won't get into details if what will happen if you don't do this. So you have run the script, you have collected all these tweets, now you can tokenize them. So as I said, tokens, it's a very fuzzy thing. I picked French for simplicity, and I decided to use an open source library to do this for me. I didn't wrote a tokenizer for this presentation. So NLTK, it will do this for you if you want to do it. It will do this for lots of other languages, including the crazy ones like Chinese, Japanese, Korean, and Vietnamese. Why crazy? They don't have spaces. So if you want to split the words, you need to understand the text sufficiently well that you know where the word starts and where it ends. And of course, there are lots of very ambiguous ways, and sometimes you can split the sentence in different ways, and the sentence has different meanings. And it's all syntactically correct. So it's a funny game, but not a game we're going to play today. Okay, so this is a very standard set. Most text data processing pipelines will do this for you generally. So you calculate the document frequencies. So you want to know the number of documents in which every token appears, at least once. And generally, there is a threshold. You eliminate every token that does not appear, that has a lower frequency than the threshold. And here it's 1 because I was very conservative. And I decided to also keep this last sentence, like, it's also a very common trick. If you do this for a living, you'll have to do it probably someday. In the same document where you store the frequencies of the tokens, usually there is a special token. It's the empty token, and this token contains the number of documents in your corpus. And this makes lots of algorithms a lot simpler. So once you have that, I picked the simplest algorithm possible to generate document vectors. It's called the Boolean model for bag of words. So bag of words means you look at all the words in your sentence. If the word happens once, at least once in the sentence, you put a 1 in the vector. And every other entry in the vector will be zeros. So the vector is of size the number of tokens in the corpus, so distinct tokens, the vocabulary, mostly filled with zeros. So for a sentence that has 10 words, there will be 10 ones in 100,000 zeros in your vector. There are lots of very smart ways to do that. TF-IDF is another way to do this, and you can actually specify this option in the script. But it's more complicated to understand what happens after. So I picked the simplest one because I wanted this to be understandable. And then the magic, so k-means. This is, again, the simplest algorithm possible to do this. It's an unsupervised clustering algorithm. So it takes a bunch of vectors. You tell this algorithm, I want k clusters. And it will group all these vectors together, saying, these 2 vectors look together, put them in the same cluster. It's one of the fastest clustering algorithms that exists. Despite this, the complexity is fairly painful. If you want to run this on 100,000 documents with maybe 100 topics, you need to be ready to wait for a while. So you need to be aware of these kind of issues. There are faster options. Mini batch is a fairly popular option. It's much faster because it can be parallelized. K-means cannot. So people do this, but this introduces lots of issues in terms of numerical stability. And again, I wanted this to be simple, so I kept the very conservative option, K-means. And I will talk about this a bit later, but the key here is what you want to do is the number of documents, presumably, that's something you cannot control. You have 1 million documents, you want to cluster them all. But the size of the vectors to represent every document, that's something you can change. I mean, so if you have 100,000 documents, maybe you have 70,000 distinct words in your corpus. So 100,000 multiplied by 70,000, that's a lot of entries in a matrix. You want to decrease the size of the vectors. And there are many reasons for that. Performance is a reason. Another one, I'll talk about it later, is it's called the curse of dimensionality. When you have lots of zeros in a vector and maybe 100,000 zeros and 5 ones in a vector, these ones, they get lost. If you want the system to do something and learn something useful, you need to do some pre-processing to make sure you don't have that many zeros everywhere. And Google for curse of dimensionality, you'll see lots of people much smarter than me talk about it. And because I wanted this to be somewhat useful, we also need a way to look at the output for this clustering algorithm. So you need to know cluster number 5, what does it talk about? Because if it contains 10,000 documents, you're not going to read these 10,000 documents to understand what the cluster is about. It's meaningless. So here I chose again, the simplest possible answer to that problem, which is you look at the frequency of the tokens in the cluster, you look at the frequency of the tokens in the corpus itself, and then you do a difference between these two distributions. And basically what is left is you take the words that have the highest difference. So these are the words that are very relevant in your cluster. They occur a lot more in the cluster than they do occur in the rest of the corpus. So I picked 10. It's completely arbitrary. So the first column is the name of the cluster. The second column is the size of the cluster, so number of documents. And here I chose 10,000 documents. I kept only 10,000. And these are the words that the thing kept for me. If you look at them, you see that there are URLs in there. I kept them. I didn't want to, I kept the simplest tokenizer possible. But you can see it already gives you a fairly good idea of what people are talking about. So this is Twitter, quite often not safe for work content. So people will talk about things that are clearly not politically correct. But if you look at some of these clusters, and I've decided to, I don't think I have this in this. Yes, okay. So there is another script in this Git repository that you can use to visualize the documents for a cluster. So you say, I want the documents for cluster 5. So this is the smallest cluster. And you'll see the documents, and if you look at this one, I did, you'll see that it's actually the same tweet that has been retweeted over and over again by lots of people. So the algorithm actually figured out that and I don't remember the actual content of the tweet. These are just words from the tweet. So don't ask me what it was talking about. The link, you can click on it, and probably you'll figure out what it was talking about. And of course, there are lots of people talking about football because that was the first week of the FIFA World Cup. I didn't take each cluster and do an analysis of what is in there. But these are fairly generic comments. If you try to do this, if you run this kind of algorithm on pretty much any kind of textual content, this is what you will get. So all the small clusters that the algorithm gives you, probably they're pretty good. If you look at them, they're coherent. So same tweets, same documents talking about the same topics. If you look at the big clusters, well, it will be a mishmash of lots of meaningless things, and you can figure out why they're together. And this is why choosing the right value for k is crucial. So there are algorithms to pick automatically a value for k if you try to find some of these on Google. But in practice, it's very hard. Even the automated algorithms, they don't work that well. So basically, when you do this, you have to live with one of two strategies. Either you generate many small clusters, and then you need post-processing steps to put the clusters together, the ones that talk about the same things. Or you generate very big clusters, and then you recluster them to see if you can find something meaningful. So these are practical comments that I wanted to do, to make now. That said, as I said, if you take this code and you run it on arbitrary content, probably you will be disappointed by the results. And there are many reasons for that. So the first one is data. More data, better. I'm not going to repeat this, but there are a couple of very famous papers that say this. If the more data you have with very stupid algorithms, and probably you'll get better results than very fancy algorithms and little data. You should consider maybe try mini batch because you want bigger data, but also you need to be careful. You don't want to lose accuracy. You can use all the clustering algorithms. Some of them work really well. Better summarization. So the algorithm I used here, this one is very stupid. There are better ways to do that. And then this is probably the most important thing that you want to do is, as I said, there's this curse of dimensionality that will work against you, whatever algorithm you choose. So you decide to use a clustering algorithm k-means or another one, problem the same. The problem is you need to decrease the size of the vectors before you feed them to your algorithm. And, well, there are lots of ways to do that. A couple of relatively common ways to do this, LSA and LDA are algorithms that you can Google for, fairly trivial to add them to your pipe, your processing pipe. They will reduce the dimension, so generate maybe 40 sized vectors instead of 100,000 sized vectors. That will make your k-means algorithm go much faster, so you can run it on much bigger data sets and so on. The other algorithm that makes a lot of sense is based on word2vec, and I'll talk about it if I have spare time after the questions. Now. Great. Now I have time to talk about the other algorithm. Yes?
If you use word2vec, then you cannot label anymore the cluster, or you basically wait to still labeling the cluster, or is it done post-processing?
So the labeling for the clusters here, it's entirely independent from the vectorization algorithm that you use. It just takes the frequencies of the tokens in the clusters against the corpus. So it doesn't matter, which is one of the advantages of this very simple approach. You can replace that. And yes, word2vec will change the results, but it will still allow you to get labels for every cluster. As I said, so here what you do is you look at the clusters. In every cluster you have documents. So for every document you have tokens. You just count the frequencies of the tokens at the end of the processing. You just don't care what you've done before. You ignore the vectors. You go back to the word representation for the documents.
for your application, do you prefer pre-training again the process, or you also consider kind of learning?
So I think you're asking, in our application, do we cluster twice or cluster once and then group things together? Option B. And that gets more into things that are things that we're still working on. But I don't have any easy answer to that question. It depends probably on your data set.
Can you give examples of why this is used in practice by people who pay you to do something like that?
So we use this for, well, lots of different things. I would need to talk about what we do before I explain how they use it. But so what we do, we sell a web-based application to brands, and they use this to do customer support on social media. So you send a tweet to Carrefour. I'm not happy about this pack of pasta. It was all spoiled when I bought it. And someone is going to answer, and they're going to answer through our application. So we receive the message and send back the answer. And we do a lot of textual processing for the messages that come in the system and to help the customer support agents to answer faster and better to us. And that said, I just wanted to give you a small, so this is the last slide. If you're interested in this, clearly the first step, and if you wanted to extend this toy example project, you do want to do this. And what I wanted to say is that this magic algorithm, it's been published in 2013, so it's fairly recent, Google paper, as usual. The more data, the better. So use a very large corpus of content to generate your model. And once you have the model, you can do lots of things, even on simple corpus. That's all I wanted to say today.